Alright, hello guys. In this presentation we'll be looking at how linear transformations are used in 3D rendering. So the first step would be to look at what linear transformations are. So what's transformation? Transformation is an operation to a vector which maps it to another vector. So basically this looks like a function. But what makes it linear? In order for a transformation to be considered linear, two properties have to be true. It has to preserve the operations of both vector addition and scalar multiplication. And here we have the mathematical representation of that. Alright, but what does this look like visually? Visually, transformations are considered linear if all lines on the grid of where you plot the vectors remain lines. And you also have the origin at a fixed point, so you don't move the origin around. And so we'll be looking at three applications of these transformations: scaling, rotation, and shearing. And here we have images of each type.
Okay, so now we're going to talk about scaling. So a common transformation is scaling, and this is the matrix that will scale points up or down along each axis. Notice how it has a scaling factor for each of the individual axes. This means that if you change this value of x, it'll scale it in the x direction, either making it longer or shorter. If you change the scale of SC, then it will the object taller or shorter. For example, if you set SC equal to 2, then you will make the object taller by a factor of 2. This is similar to extruding an object for those who are familiar with SolidWorks. Here's an example of scaling along the x-axis. So what's actually happening here, at every point along the cylinder, the coordinates of that point are being multiplied by the scaling matrix to get the new coordinates for each of the points, and then each of those points are being displayed on the screen as a solid object, and that is what you're seeing on the screen.
Alright, so now we'll be looking at rotational motion. Rotation motion on a 2D graph can be visualized as having a point with a fixed distance away from the origin, but allowing that point to rotate around the origin, keeping that fixed distance intact. In the bottom figure, we can see both the red and green lines have a similar length, but the red line is rotated a certain amount of degrees away from the x-axis, thus giving two new points, x1, y1. So how do we go from having these two original points rotating around a certain amount of degrees and getting these two new points? Well, to get these two new points, you'd have to multiply it by a transformation matrix. This transformation matrix comes from the equation above, which show you how to get the two new points. So as you can see, you take the two original points and multiply it by the transformation matrix, in which you input however many degrees you'd like to rotate around the origin, and the result should be the two new points. So that's how it works in 2D motion, but in 3D motion you'd have to use these other sets of matrices, or transformations, depending on which axis you'd like to rotate on. As you can see, rotating around the z-axis looks a lot like rotating around the origin in 2D motion. This is because in 2D motion, you basically are rotating around the z-axis.
Shearing is another linear transformation utilized in computer rendering. Unfortunately, shearing in 3D is a bit harder to visualize, so let's look at it in 2D first. A shear transform sort of skews everything along a certain axis, like in this example where a square is skewed along the x-axis and ends up like a parallelogram. A cool property of a shear is that its effect can be varied independently for each axis. Here's some animations to better illustrate what happens as the shear is adjusted for each axis in a 2D environment. Now that we've seen what a shear looks like in 2D, let's look a bit at a shear in 3D. The same principles apply here, there are just more parameters to control. In the general format shown here, adjusting SHXY will change how the x-axis is sheared in the y direction, while similarly, adjusting SHYX will change how the y-axis is sheared in the x direction.